Bob Westervelt. Today, we're lucky to have Jyoti Katoch at the Department of Physics in Carnegie Mellon. She did her PhD at the University of Central Florida and went on to do a postdoc and then research scientist position at Ohio State before going to Carnegie Mellon. What she works on is sort of very interesting system is stacks of 2D materials such as graphene that offers the opportunity because you can actually stack them up and get a quantum material which like a superlattice, only it's only 1 atom thick, with properties that you can't get out of 3D materials by twisting it. And this is something that's very tough to do in 3D, and so you actually end up with new quantum states and entirely new types of behavior. And so she's using a surface probe, ARPES, to look at the electron states there. And that's what she's going to tell us about today. I look forward to it.
Well, thank you, Bob, for the introduction and invitation to present my work here. I'm going to talk today about probing the two-dimensional material using focused angle-dissolved photoemission spectroscopy. Okay. So before I begin my talk, I just want to introduce my young group at Carnegie Mellon. It's a liquid group. It's a lab for investigating quantum material interfaces and devices. And what we are interested in is investigating the intrinsic electronic properties of novel quantum materials, such as two-dimensional materials or 3D Dirac semimetals. And the idea is to provide additional on-demand functionality using external perturbations such as add atoms or substrate and strain engineering. And so for this, to accomplish this goal, we are building a system where we can do a material synthesis, so using molecular beam epitaxy, and then we can transfer a sample using this transfer highway, sample transfer highway, and take it to this in-situ characterization chamber where we can do magnitude transport measurements. So we have capabilities like magnetic field up to 9 Tesla, and we can do both in-plane and out-of-plane, apply both in-plane and out-of-plane magnetic field. We can do the in-situ device fabrication using shadow mask and sputtering. And we can also put our atoms like alkali metals or hydrogen atoms onto our devices. And we can also do in-situ Raman and photoluminescence measurement. So it's a unique experimental setup that we are setting up at in our lab here at Carnegie Mellon. And this is my vision. And so far we have made a good progress in the last 2 years. We have a fully operational MBE chamber, and we are growing currently epitaxial thin films of sodium bismuth, which is a 3D Dirac semi-metal. And the in-situ magnitude transport chamber is also coming along, and we are hoping in next 10 days we'll be able to test and do our first device measurements in there. But today, in my talk that I'm going to talk about, it's focused on this focused angle-dissolved photoemission spectroscopy. And for doing these measurements, we actually go to beamlines at different synchrotron facilities. And primarily, we use the Advanced Light Source and the Diamond synchrotron in UK. And so this is a brief outline of my talk. I'm going to give a very brief introduction about two-dimensional materials and why they're interesting. And then I'm going to talk about mainly 3 of our work where we used photoemission spectroscopy to probe the many-body physics in two-dimensional materials. Okay, so let us begin with why we are in particular interested in 2D materials. The world of 2D material has expanded in the last few years, and now we have hexagonoboronitride, which is insulator. We have semiconducting materials like MOS2, WS2. We have metals and also superconductors like niobium selenide. And all these materials, they have unique electronic and optical properties, and one could think of integrating them into thin layers to form 2D flexible, faster, higher, this energy efficient variable electronics one day. So there are a lot of applications that can come out of these 2D materials, possibly. Now, Feynman, in his famous lecture, there's plenty of room at the bottom. He talked about, what we could do if we have layered structures with just the right layers, and if we could really arrange the atoms and control the atoms on the small things. And it turns out that we can precisely do so with the 2D materials, because just like how we can, build different, use the Legos to build different structures, in the same way, we can take these two-dimensional materials and stack them vertically and create these novel materials. And we can engineer interfaces with atomically sharp interfaces. So, this is a really unique opportunity where we can actually do material design depending on what kind of application you need. Now, in addition to this, we can also stack different 2D materials in a way that they have, in a way that we can, tune the properties of these two-dimensional material based on the twist angle between the layers. And so here I'm showing an example. So we have 2 graphene layers which are stacked on each other, and you can see just by stacking, we can create these Moiré pattern or Moiré potential. And what happens is that the electron in such a heterostructure can no longer move freely in the planes of these atomic layers, but are trapped, in the spatially periodic potential energy variations of this Moiré potential. And so we have seen, recently a body of work where first it was shown that by just, stacking graphene on HBN, it can generate these secondary Dirac cones. And as a result, in the transport measurement, you can see these, these satellite peaks appear. And if you stack 2 graphenes to form this bilayer, and if you do so at a magic angle, then you can get Mott insulating and superconducting states. And in TMD's heterobilayers, we can actually observe interlayer quasi-particles. And so, so the 2D materials are truly exceptional, right? And so now the question is, can we actually can we investigate them, these 2D materials and their heterostructures with a tool that can directly see the electronic structure and the many body effects in them without any assumption? And it turns out that, we know ARPES, it's a powerful technique which we can use to directly probe the occupied electronic states by measuring the dispersion of the material. And it is based, and this technique is based on photoelectric effect, where if we shine the sample with a photon beam, then electrons are ejected out, and the kinetic energy of these ejected electrons is given by this equation, where EB is the binding energy and phi is the work function. And so in ARPES, both the emission angle and the kinetic energy of the escaping electron is measured, and from there we can obtain the band structure. Now, I don't have the time to go over the, the theory of the photoemission process, but I want you to keep in mind 2 important things. The first one is that the photoemission intensity, it is directly proportional to the Fermi-Dirac distribution function. And secondly, the single particle spectral function in ARPES, it gives us the band structure and the interactions. And here the interactions are captured by this imaginary self energy term, okay? And I'll come back to this later in my talk, where I'm going to look at this imaginary self energy term in the single layer graphene. Okay. And this is great, but if you think about it, traditionally ARPES has a very large beam spot size, which means that you can only investigate or look at the electronic band structure of millimeter size samples. But typical 2D materials or the heterostructures, they have a mesoscopic size. So it means that if we want to probe their electronic band dispersion, then we need a next generation ARPES frontier. Or focused ARPES, focused or nano ARPES, And so my group primarily uses the nano ARPES and station at master beamline at advanced light source, where with the zone plate, you can actually achieve a spatial resolution reaching up to 120 nanometers. And so now, now the first step for doing ARPES measurement or nano ARPES measurements on these 2D material is to find a substrate that would be ideal for doing these measurements. And it turns out for doing our ARPES studies, we need an ideal substrate to have these properties. It should be free of charge impurities. It should be a flat substrate so that it forms a very smooth interface with the 2D material and doesn't cause additional scattering. And it should have low screening so that you can obtain useful information. And from the transport measurements, we know that HBN is a very good substrate for 2D materials. The only problem is that it has a large band gap of about 6 eV. So it means that if you try to do ARPES measurements on bulk HBN, then you will get a lot of charging issues. And so in order to circumvent this, what we did was we exfoliate or thin down the HBN and put it down a conducting substrate. And so here's an optical image of our exfoliated HBN flakes on a titanium oxide substrate. And so here the thickness of the flake is about 30 nanometer. And as you can see, we can now get the dispersion of the HBN along the K gamma K direction. And so here I'm showing just a comparison of the single layer WS2 on 3 different substrates. So here's the dispersion along the K prime gamma K direction for single layer WS2 on silicon oxide substrate. And in the middle, we have it on the titanium oxide substrate, and on the right, I have it on the HBN. And as you can clearly see, we have the sharpest band when we have WS2 on a HBN. And it is not kind of surprising because we know that on silicon oxide substrate, there are a lot of charge impurities, and also it's not atomically flat, right? So because of that, we get a lot of a broadening of these bands. And similarly on titanium oxide substrate, what can happen is that because of the photon beam, there can be a lot of oxygen vacancies, which can again, cause the broadening of the bands. And so now that we have established that HBN is a good substrate or I should say thin down HBN or a few nanometers of HBN is a good substrate for the 2D materials to carry out ARPES studies. I'm actually going on and I move on to my first study where we used potassium atom to induce quasi-particle driven novel phenomena in single layer WS2. Now, before I jump into my into what we did, I just want to do a very quick, go over very quickly why the transition metal dicogenides are very interesting. Now, they have this chemical formula MX2, where M is the transition metal and X is the chalcogen atom, and the transition metal is sandwiched between the 2 chalcogen atoms. And we have about 40 different layered TMDs, which have all diverse electronic properties. But what we were interested was is the semiconducting TMDs like WS2, because in them, we have an interesting transition from indirect band gap to a direct band gap as we thin down the sample. And in addition, because it has a very heavy metal atom, we see that there's a splitting in the valence band. And for WS2, the FT calculation shows that it can be about 433 MeV. And in addition, because of the inequivalent values in the single layer TMDs, we have an additional valley degree of freedom. And we have this spin valley coupling, which means that if we use the light of positive helicity, then we can couple the carriers in the one valley. And if we use the light of the negative helicity, then we can couple the carriers in the other valley. And in addition, because of the broken inversion symmetry, in TMDs, we can also, in single layer TMDs, we can also have a novel Hall effect called valley Hall effect. So as we know in the Hall effect, if we have a current carrying conductor and we apply a perpendicular magnetic field, then the charge carriers, they can experience a force due to this magnetic field, and they can get accumulated on the sides of the sample. And this can give rise to this Hall voltage. Now, similarly, in TMDs, when we apply an in-plane electric field, then the electrons in the different valleys, they experience opposite Lorentzian force, and so they move in the opposite direction, which is perpendicular to this. So they move in the opposite direction, which is perpendicular to this drift current. In addition to that, the TMDs also have a very strong Coulomb interactions, which means if we excite the carriers from the valence band to conduction band, then this electron and hole, they can form a strongly bound quasi-particle called excitons. And if we n-dope our sample by putting a lot of electrons, then we can have a situation where we can also have a very strongly bound electron hole, or hole electron complex formation, and these bound particles are called tryons. And both excitons and tryons, they have been observed in the optical measurements. And so the question that we had was, can we unlock these excitonic and tryonic effects in our in a single in this WS2 using ARPES? And it's very interesting because now it was also shown that you can have similar to Valley Hall effect, we can also have the exciton Hall effect if we have a temperature or a gradient or a chemical potential gradient. So in order to study this, we fabricated a single layer WS2 sample on titanium oxide. And so here's the side view of schematic of my sample. So we have a single layer WS2, and this was a CVD grown sample, and it was transferred on HBN, which was sitting on a titanium oxide substrate. So once again, this titanium oxide substrate is n-doped, so it's conducting. And just so that in order to make sure that we don't have any charging effects, we drape our sample, this WS2 sample, and around the HBN so that it's touching the conducting substrate. Okay, so here is the optical image of our sample. And here's the corresponding photoemission intensity map of the same area. And so here at each pixel, we actually measured the dispersion of our sample. And so so there's an enormous amount of information in this photo intensity map. And one thing that you can clearly see is that this HBN flake that we have that is partially covered with a single layer WS2, we can clearly see it in this photoemission map, photo intensity map. And one thing you will notice is that there is also a lot of variation in the quality of our sample. And so, by generating these kind of XY maps, it also allows us to, optimize and find a spot where we have the best quality sample and then carry all our experiments at that spot. And so here we use the micro ARPES, so where the spot size is was about 10 to 12 microns. And so so we did, in this study, we did all our measurement at this spot which I'm showing here by this white arrow. And you can see, so here's the dispersion of the single layer WS2 along the K gamma K direction. You can see we have a very sharp bands, and we see a splitting here, and we can clearly see the splitting in the valence band. And here I'm showing the dispersion of the HBN along the HBN K prime gamma K direction. And so by taking these constant energy cuts, which I'm showing here on the right, we can also extract what is the twist angle between our samples. And what we found here was that we have very weak interlayer interaction between our single layer WS2 and HBN. Now, let me show you what happens when we actually put potassium atoms on our sample. And so when I say we are putting potassium atom, what we are essentially doing is we are putting a lot of electrons in our sample. And so here's the dispersion along the K prime gamma K direction. And this is for undoped sample. And so And here on the right, I'm showing what happens when we dope it with potassium. And so you can see the conduction band appears. If you look carefully, you will see that as we dope more, so this is more doping, something is happening at the K point, and not much is changing at the gamma. And in order to see what is happening, what we can do is we can take the line cuts. And so we can take the line cut for the undoped sample and also at the highest doping. And this is what I'm showing here in this graph. And we see very interesting thing. We see that the splitting in the valence band here for the undoped sample is about 430 MeV, which I'm showing here. But at the highest doping of the potassium, we observe that the splitting actually increases. And so we will go from 430 MeV to about 660 MeV. And also we observe that the band gap decreases. So it was interesting because we observed that the spin orbit splitting here is increasing just by electron doping. Now, in order to see what's going on, next I'm going to look at what's happening at the K point in much more detail. So once again, this is for the undoped, and now here I am showing as a function of dosage. So you can see here we are increasing the dosage, and at the K point, we can look at the features much more clearly if we again take the line cut for the undoped sample and at each of these dosages. And again, once again, I'm plotting here the binding energies for these as a function of the K potassium dosage. And so this is for the undoped sample. And you can see after the first dosage here, we observe a rigid band shift to higher binding energy. So the conduction band, it shifts to a higher binding energy, and we can see it now. And both these two branches, the upper branch and the lower branch, so this is the upper branch and the lower branch, which I'm labeling as VBA and VBA. You can see that both these branches, they shift to a higher binding energy as expected. But interestingly, when we dope more, the conduction band, it is shifting to a higher binding energy, but these two branches of the valence band, they actually start shifting to a lower binding energy. And on more and more dosage, we notice that this branch, upper branch of the valence band, this upper branch, it actually shifts more as compared to the lower branch. And this is what I'm showing here in these two plots. So here we have the splitting as a function of dosage. And you can see that, in this range where we have dosages, electron density of 10 to the power 12 to 10 to the power 13, there is not much change to the spin orbit splitting separation. But as we dope more and go higher than 10 to the power 13 dosage, the splitting, the splitting actually is increasing. And similarly, we observe, if you look at the separation between the conduction band and these two branches of the valence band, we observe that at higher dosages, these separations, they start to decrease. And so what's happening here is that the spin orbit splitting, enhancement is actually happening when we are putting a lot of electrons, which means that the origin is, is the many-body interactions in the system. And we can understand this more if we look at what is happening at the high dosages. And if you pay really good attention, you will see that here in the upper branch here, we have actually a kink. And it turns out if we can understand the origin of this kink here, then we can understand why we are seeing an enhancement in the spin orbit splitting. And so I'm going to give you a hand wave, like a simple picture of how we understand, or what we understand is happening here. So in the ARPES, when we shine light, we get this photo hole in the valence band. And now when we put a lot of electrons in our system, then we can end up in a situation where near the Fermi energy, we have electron hole pair, and this electron hole pair in the conduction band can interact strongly with this photo hole in the valence band. And then because of the strong Coulomb interactions in this system, in these single layered WS2, then they can form this charged electron hole complex, or which we call trion. And so we believe that trion formation here leads to renormalization of the renormalization of the bare bands and causes this enhancement of the spin orbit splitting. And so I'm going to conclude this part of my talk by saying that, we in the study we successfully showed that we can use micro ARPES to access the electronic properties of these complex mesoscopic size heterostructures, and using potassium doping, we investigated the band renormalization driven by these many body interactions in single layer WS2. Okay, so I just showed you that in ARPES, we can tune the Fermi level by, alkali metal doping. And this is great, but this process is irreversible and uncontrollable. And add atoms, they can cause impurity scattering, which can result in, increased in the measured line widths and make it difficult to separate, from the intrinsic effects or intrinsic interactions. And we know from the transport measurements that in the devices, we can tune the charge carrier density in a non-invasive way by using this electrostatic gating. So, and this process is reversible and we have much better control. So in the last 2 years at Carnegie Mellon, we have been pushing in operando nano ARPES measurements on fully functional devices. And in such a setup, we can simultaneously measure the energy and the momentum dissolved electronic band structure of the 2D materials while we're applying backgate voltage or passing current to the sample. And so now I'm going to show you our in operando nano ARPES results, where first in the first study, we demonstrated a tunable many-body interactions in graphene devices. And here, the spot size for our ARPES was about 2 microns. And so here's the schematic, here's a side view schematic of our device, where we had a graphite backgate. And here are the optical images, optical image and the ARPES intensity map. And once again, this ARPES intensity map, it carries enormous amount of information because we measure the dispersion at each of these pixel points. And you can clearly see that we have a graphene here. And if I go in this yellow marked region, I can see the sharp Dirac cones of the graphene. And the band here at 2.5, it corresponds to the HBN. And this, if you look carefully, you can also see there's a faint bands here, which I'm pointing with these pink arrows. And these are formed due to the mini Brillouin zone of the graphene HBN superlattice, as we had a twist angle of about 2 degrees between our graphene and HBN. So next, let us look at the detailed dispersion of the Dirac cones with gate voltage. And so by tuning the gate voltage to negative voltage, I can p-dope my sample. And by tuning the gate voltage to the positive gate voltage, I can n-dope my sample. And I can now get access to the conduction band. And if you look at this 8 volt here, you will see that the conduction band and the valence band are no longer touching each other at a point. And to see it much more clearly, what I here on the left plotted is the dispersion at 10 volts. And I'm labeling the valence band as V, and I'm labeling this conduction band as C. And the points at which these valence band and the conduction band, they are crossing each other, I'm labeling this. So the valence band is crossing here, and I'm labeling this as EDV, and the conduction bands, they're crossing here, and I'm labeling that this as EDC. And I'm going to show you next few slides that by tracking these 2 crossings, we can extract information about many-body interactions in our sample. And our work shows that what happens to the electron hole excitation at finite doping in devices, which are typically measured in the transport studies. Okay, so what I'm showing here is a graphene Fermi surface at few gate voltages. And the this radius here, Kf, that determines the size of the Fermi surface. We can extract this by actually taking a line cut here at the Fermi level, the Fermi surface, and plotting these MDCs, which I'm showing here. And so the peak, the separation between these two peaks, from here we can extract this radius Kf. And if I, and furthermore, I can track this, these two crossings, the conduction band and the valence band crossing, by taking a line cut along this green line here. And I can plot these EDCs, which I'm showing here. And so so there here the EV is the peak EV essentially the V branch crossing. And you can see that this peak remains fully above, below the Fermi level in our spectra for all gate voltages above 1 or equal to 1 volt. And this C branch crossing, which is denoted by, which is this peak here and denoted by this EC, you can see it is separated in binding energy from this peak. And it remains below the Fermi energy for all gate voltages equal, greater than or equal to 3 volts. And so what we can do is we can plot this radius Kf and these two peaks as a function of the gate voltage, which I'm showing here. And also we can plot this different separation between these two crossings, which is this gray data points. And what is interesting is that this doping dependent, separation of the Dirac these crossings, it shows us that the metal-body interactions are contained in the photohold spectral function. And in order to investigate this further, how they are, how's the doping dependent these many-body interactions in our device, what we can do is we can fit these MDCs much better and extract a more precise estimate of the binding energies of the Dirac crossings. And this is, and then we can plot it as a function of the charge carrier density by using this relationship. And this is what I'm showing here. So these red data points that I have here, these are for the conduction band crossing, and these blue ones are for the valence crossing. And you can see that we have here, the fitted curve here are, they have a square root n dependence. And what is interesting is that we find that the separation between the Dirac crossings, it vanishes here with the charge relativity point, and it increases as we go, with the higher doping, whether we do N doping or we do P doping. And this is interesting because previously in an ARPES study, it was shown that if you N-dope the quasi-freestanding graphene, then you get the same kind of behavior. And so in their study, they actually used the potassium add atoms, so they could reach a much higher charge carrier density. And you can see that they actually see a diamond-like feature here. But the charge relativity point, but this is something we couldn't observe because we are at a lower charge carrier densities. But clearly, in their study, they attributed this to the plasmaron particles, which are the bound states of charge carriers with plasmons. And so in our study, we see a clear evidence for electron plasmon excitations, and we can convert this separation between these two Dirac these crossings into an estimate of how effective the Coulomb coupling constant is. And if we do that, we find that for our samples, we have a coupling constant of 0.5. And this is the same coupling constant that was observed for this quasi-freestanding graphene. And even though the value of alpha looks small, but we find that electron-electron interactions can be rather large, as was seen in this previous study. And just for reference, for suspended graphene, where it is fully unscreened, the coupling constant was estimated by these two studies to be about 2.2. Okay. So next, I'm going to show you how the interaction strength in our device affects the doping-dependent shape of the Dirac cone. And we can do so by extracting the Fermi velocity near the, at the Fermi energy, Fermi level, Fermi energy, and then we can do the extract this band velocity below this Dirac crossing. And I think we did it around at 300 milli eV below the Dirac crossing in the valence bands. And I am showing the Fermi velocity here. So these are the orange data points that you see here. And we also did the theoretically fitted for our alpha value of 0.5. And this is what you see in this orange curve here. So this is a fitting. And what we see is that for our device, there is this sharpening effect, right? There's a sharpening effect towards charge neutrality, which is what you would actually expect for a suspended graphene spectrum, as was previously shown in 2019. Moreover, when you have alpha approaching 0, which is this fully screened limit, we get this non-interacting velocity, which is shown here by this horizontal line. And for the band velocity, which is the star, we find that there's a continuous decrease of the velocity as the Dirac cones, they are shifted to higher binding energy with the increasing electron doping. And so this is due to the fact that we have, electron hole pair scattering processes at a higher binding energy. So this is expected. And so our results here, the take-home message is that our results here confirm that quasi-particle velocity in gated graphene on HBN is doping dependent, and it is due to these Coulomb interactions. And next, we can actually also look at the doping dependence of the imaginary part of the self-energy, which I'm plotting here. And we can extract this from the line widths of these Lorentzian fits to the MDCs at the Fermi level. So if we just do the peak, the fitting here, we can do, sorry. Yeah. So, and so and what we observe is that this imaginary part of the self energy, it actually is suppressed. So it's suppressed here near the charge neutrality point. And then it follows this, and it basically increases both for N doping and P doping, and it follows this square root N dependence. And this is consistent with the short range scattering. And so short range scattering is where we have this electron defect scattering, or we have electron phonon scatterings. And in our sample, we actually also measured, we could extract the mobility, which was around 6,000 centimeter square volts per second at room temperature, which is not, which is reasonable, but not, it's not a whole lot. And we believe that this the mobility in our. I would like to conclude this part of the my talk by showing that we were able to do inner nano ARPES measurements on graphene devices, and we demonstrated that by simultaneously measuring the transport properties and doping dependence of the quasi-particle spectral function, and this provides us access to many body interactions for a wide range of energies and momentum. Okay. Next, I'm going to move on and show our latest results on probing the correlated states in twisted bilayer graphene. Okay, so the Van Hoof singularities we know is of interest, especially if the Van Hoof singularity is at is close to the Fermi energy, as we then have an increased density of states, and this can result in enhance electron correlations. It can trigger ordering instabilities such as superconductivity or even charge density waves at low temperature. And in graphene, the Van Hoof singularity at M point is so far away that it is not possible to reach it in the transport measurements using the electrostatic gating. And so we saw that, if we stack two graphene layers, then the rotated, these two Dirac cones, they hybridize and they form the superlattice Van Hoof singularities, which with energy that can decrease as the twist angle between them increases. And so in twisted bilayer graphene, we've seen that at a magic angle, we can get superconductivity. So interesting correlated phenomena. And so to investigate the effect of the gating on the energy and the momentum dependent correlations of interlayer hybridization between these Dirac cones of the twisted layer, we fabricated twisted bilayer graphene devices where the twist angle was about 12 degrees. And this corresponds to a Brillouin zone reciprocal lattice vector of about 0.63 Armstrong inverse. And this is, and the important thing I want to point out here is that this is about 11 times larger than the mini Brillouin zone that you would get for a magic angle graphene. And so which means is that if we choose a magic, like a graphene with a magic angle, a bilayer graphene with a magic angle, then the momentum dependent line weight of the features would become very comparable to the size of the mini Brillouin zone, and it would make the detailed analysis of a feature within the single Brillouin zone impossible. But in our study, we have a larger 11 times larger mini Brillouin zone, and so we can do a more detailed analysis. And this part of the measurements, they were done at Diamond Synchrotron in UK. And so here I'm showing the ARPES spectra for 3 different gate voltages. And these are along the line connecting the K points of the top and the bottom graphene. And you can see at 12-degree twist angle, we have a spectra with 2 separated non-interacting graphene Dirac cones at low binding energy. And these cones, they look like they start to hybridize around 1 eV. And we have here we see that the Dirac cone of the bottom layer is less intense, and this is because of the attenuation of the photoelectrons through the top layer. Okay, so next, look at the mini Brillouin zone, and that is what I'm showing here. And here are the constant energy cuts of this mini Brillouin zone, and I'm labeling here the high symmetry points with these colored dots. So if here the KBD, it has a blue dot, so correspondingly here this K point of the bottom graphene is here, and this is denoted by this blue dot. And so as you can see, at Fermi energy, we start with at Fermi energy here, we start with 2 isolated Dirac points, right? And at the binding energy of 0.95 eV, what happens is these 2 points, they start touching and each other at this point, which is the M by T. And if we go to higher binding energy of about 1.40 EV, what happens is the cones, they start to fully hybridize, and they form these knot-shaped contours around the around the M prime, M BT, and M. And these are the signatures of hybridization between the main Dirac cones and the mini cones emerging from the these K and K prime points. And so next, what we can do is we can look at these at the dispersion along these directions. So gamma MBT and gamma M prime and this gamma M. And this is what I'm showing here. And as you can see, we observe downward curving bands, which match with the theory DFT calculations pretty much. And similarly, what we can do is now we can look at the dispersion along the this direction, which is KB, MBT, KT, and similarly along this direction and similarly to this direction, which I am showing here. And here what we observe is that there is a upward curving bands. And again, these bands, they match with the DFT calculations. And next, what we can do is we can take the ADC cuts like around these M point in the orthogonal direction. And when we do so, it reveals that we have these Van Hoof singularities and mini gap. And the mini gap here is about 300 milli eV. And the horizontal line here, it shows the marks the maximum energy below mini gap. And so next, I'm going to show here the ARPES intensity cuts along the M prime of the neighboring brilliance zone. And what we see is the flat band here is observed around the superlattice Van Hoof singularity at a lower binding energy, and we see another flat band at a higher binding energy. And actually, you can see this much more clearly if we integrate the photoemission intensity in the two orthogonal direction of the milli-brilliant zone, and so here. And this is what I'm showing here. And so you can actually see the peaks due to the flat bands here and here. We observe two flat bands, and this flat band at a higher binding energy, this comes from the bottom graphene Dirac cone, where it crosses, again, it crosses the branch of the top Dirac cone, and it is attributed to the dispersion around the endpoint of the main brilliance zone, where the Van Hoof singularity of the isolated graphene occurs. So next, let us look at how the flat bands and these Van Hoof singularity, they shift with the gate voltage. And so here is the ARPES spectra along the K points of the bottom and the top graphene Dirac cones. And you can see the Van Hoof singularity, it shifts to a lower binding energy as we hold dope our sample by applying a negative gate voltage. And we can track this better if I plot them here by plotting them as a function of this charge carriers in the bottom graphene layer. And so here I'm showing it for all the three Van Hoof singularities, and what we observe is that they have a square root n dependence, and this mini gap, the mini gap, it basically it remains constant. And similarly, we observe, a same square root n dependence for these flat bands. And interestingly, we find that this flat band at a higher binding energy, this can be tuned by doping more, like almost double as compared to this lower flat band at a lower binding energy. And this is due to the combination of the fact that we have different charge induced in the two graphene layers, and the shifting in the, as I said before, the shifting here and the higher binding energy for the higher binding energy flat band is taking place in a highly nonlinear, collinear part of the bottom Dirac cone. Furthermore, what we can do is from our data, we can extract and plot the phase diagram, which describes the Van Hoof singularity binding energy with respect to the Fermi energy as a function of the twist angle and the doping of the bottom graphene layer. And so our results here, they establish a route towards accessing this emerging phenomena associated with Van Hoof singularity physics for a wide range of superlattice heterostructures. And so I would like to conclude by saying that, this part of the story by saying that in our nano-ARPES study, we were able to identify the Van Hoof singularity locations and the flat bands in our mini band dispersion of the twisted sample. And by electrostatic tuning, doping our two graphene flakes, we were able to track the energy and the momentum dependence of these features in our sample. And in the end, I would like to acknowledge the funding sources and the collaborators. I especially want to thank the beamline scientists at Advanced Light Source and at Diamond Light Source. and our our collaborators at Naval Research Lab, who provided us the CVD samples, CVD single layer WS2 and graphene samples. And thank you.
Well, that's great. Very interesting results. Any questions? The way you can ask a question for the audience is to put it in the chat clicker on the bottom of your Zoom window.
Thank you.
Okay. Here's a question from Christina McGann. What strategy do you use to get 2D materials with patterned electrodes from Carnegie Mellon to ALS with while maintaining sample purity defects from the air, moisture, et cetera, minimizing the risk of static discharge, destroying devices in transport? Always challenging for me. I know I've destroyed devices myself.
Yeah,
no,
it's really challenging. Yeah. One thing we've done both the things actually. So we have made devices here and not wire bonded them, and taken them at ALS and then wire bonded it there and then measured them. But for the diamond, when we went to diamond synchrotron, we actually also did this thing where we wire bonded it here and shipped them. And fortunately, this arrived. But in general, I would say, for 2D materials, so far we've done work where, they were not air sensitive. So it was not a problem, and we do, when we take them over there, we do anneal them, which, by heating them. So we anneal them in ultra high vacuum. And so that helps to get rid of any adsorbed gases or water on the surface. But recently, so actually we have beam time next week, and today my students, they are shipping really air sensitive material, which is the sodium bismuth, which we cannot even take it out in the glove box. So it's that air sensitive. So in order to measure their ARPES spectra, what we are doing is we're shipping a UHV suitcase. So the samples are in a UHV suitcase, and so today my student is supposed to ship them, and so it has a small ion pump, which is a battery pack backed by the battery, and once they receive it, they are going to attach it to the beam line directly, and basically just measure them.
Okay. I see. It's not entirely trivial.
Yes. So I saw the message from Christina. She's asking if your wire bond survived the anneals, and the answer is yes. We do it all the time, actually, because, as I said in the beginning of my talk, we actually have done a lot of transport measurements where we put add atoms on the surface. And, if you want to do that, then you have to make sure that your surfaces are atomically clean. And we always, after wire bonding, we put the sample inside and we anneal it in ultra high vacuum. I've done it at 12 hours for graphene samples at about 150 C, and it survives.
All right, great. Other questions?
Thank you, Christina.
Okay, if not, thanks very much. These are very interesting results. It's nice to see that people can get this much information. It's the kind of thing we're trying to figure out.
Yeah,
but
thank you so much.
Thank you. Yeah. Thank you very much.
Okay.
Bye-bye. Bye, thank you.
Bye. Thank you.